This video will cover section 7.2a, which covers cross-sectional volume. So we're obviously finding volume of shapes now instead of just areas. So to think about cross-sections, I'm going to look at a hard-boiled egg. So we have two pictures here. We have one egg that's been cut vertically, so you see the cross-sections of that egg is going to look more like an oval shape. And then I have an egg that has been cut horizontally, and those horizontal slices are actually more like almost perfect circles, really. So what we're really going to do in calculus is we're going to look at the cross-section of a figure, and we're only going to look at known cross-sections. So those are figures that we know how to find, like the area of. So a circle, for instance, or a square, a triangle, things like that. We're not going to get into crazy cross-sections right now. So if I know the shape of the cross section, so let's say the egg that's been cut horizontally, so we have like almost perfect circular sections here. And let's say I wanted to calculate the volume of that egg. Well, all I would have to do is find the volume of each of those pieces. If you think of each of those pieces as really a very, very thin cylinder, so like really a circle with a very small width to it, and I were to add up each of those slices, then you could get the volume. And that's really what we do when we integrate. That big integral symbol really means adding up something. So we're going to add up each of these slices that have this really, really small width. So actually what I'm going to do here is I'm going to draw a diagram. So let's pretend that I've actually sliced one of these egg slices in half like that. So that's what I've kind of drawn here, and kind of looking at it from the side. So now we have a semicircle, and you see that it has this kind of width right here. So if I were to think of this as an integral and I wanted to actually find the real volume of this egg, then what you're actually wanting to do is make that width approach an infinitesimally small width. So just like when we were taking Riemann sums, an actual integral would be those rectangles, and a Riemann sum would be infinitesimally small. And what we end up calling that infinitesimally small width is dx, or now that we've learned, we can also call that dy. So if you think of that width as dx, so as those egg slices get smaller and smaller and smaller and infinitesimally smaller, then really what you have is going to be an actual flat circle. So what happens is if I add up an infinite amount of circles, then you're going to get the volume of this egg. Okay, so like I said, we were talking about known cross-sections. So an egg has cross-sections of circles. But what we're going to look is actually at flat surface area, so figures that you can lie flat on a surface. So for the egg, we'd have to cut it in half in order to get that flat surface. So the cross sections would be semicircles. All right, so the known sections that we're going to be looking at are squares. So what we're going to do is we're just going to, before we get into the calculus, just talk about the formulas for the areas of each of these cross sections. So if I have cross sections of squares, and we're going to call that side length S, then that's going to be an area of S squared. All right, then we're also going to have cross sections of equilateral triangles with side length S. And we could sit here and derive the formula for the volume or the area of an equilateral triangle. Some of you may already know it, but it's root 3 over 4 S squared. This is an equilateral triangle with side length S, not with height S, so therefore it's not 1/2 base times height. Then we're also going to have cross sections of rectangles with a length of S and a height of H. And then we have an isosceles right triangle with a leg of S. And so if it's isosceles, then it's both of its legs are S. So that is going to be 1/2 base times height, which is 1/2 S squared, since the base and the height are the same. And then the final one is a semicircle with diameter S. And again, we're not going to spend the time to show you where the formula comes from. But again, some of you may already know it. So if I have a diameter of S and I was to find that area, then you're going to have pi over 8 S squared. Okay, so we're going to take each of these cross sections and we're going to kind of place them on top of a flat area that can be bounded by different functions. So for instance, like the egg, if I made like an egg-shaped function, then you would have something like that sitting flat on the surface. So if you're like looking down at an egg sitting on a like a piece of graph paper or something, then it would look like that. And then let's say that we were going to slice this egg up into horizontal cross sections. So we're going to make little cross sections that are going to be semicircles. Okay, so then those semicircles are going to kind of come out like that. All right, and make that egg-shaped format. So we have this two-dimensional figure that's the base, and then these known cross sections are going to kind of like come out at you to create a three-dimensional figure with a flat base, where that flat base is bounded by some curve on a graph. All right, so let's look at an example. So we have our nice friend, Emmanuel the duck, to come back and help us learn about cross-sectional volume. So Emmanuel the duck just bought land with a perimeter set by these functions, negative x squared plus 2, x equals 0, and y equals the square root of x. I'm going to graph those really quickly. Okay, so here's a quick sketch of what this would look like, and I've just done the bounded region. So I'm not doing the rest of the curves, I'm just doing what the bounded region would be like this. Okay, so let's say that Emmanuel the duck just bought land with a perimeter set by what we see there. So his plot of land looks like that if you're looking at that from an aerial view. Then he plans to build a barn which uses the area described above as the base. So he's going to like build a barn on the whole property of his land. The barn will be built up so the cross section's perpendicular to the x-axis. That's important to see because now these problems are telling us how we're going to take that representative rectangle that we were talking about before when we found area between two curves. So perpendicular to the x-axis, that would be a representative rectangle that would be vertical. Okay, so I'm going to draw my little representative rectangle just like I did before with area. And those cross sections are going to be squares. So that is, if I were to kind of take that side length, so this red rectangle that I drew, that's going to be like my S, like we had up above. And so that S determines how tall my squares are going to be. So where I've drawn this, that length of that square is going to be the same as the height of that square kind of coming out at you. Okay, so it's going to be this square here for that particular representative rectangle. Now, if I drew a different representative rectangle, let's say like here, then I'm going to have a much smaller square that looks like that. All right, and then of course, if I have a much bigger rectangle or a different one here, then we're going to have a bigger square. Okay. And I apologize for the poor drawings, guys. I'm doing this on a tablet instead of on the board, so my drawing's not as pretty as it normally is. Okay, so what's going to happen is you're going to have all these squares, and you're going to add up a bunch of these squares, and they're going to be different sized squares. And if you can kind of visualize it, it's going to look kind of like a square cornucopia, that thing at Thanksgiving that's filled with all the fruit. So it's going to be really big up here, and then it's going to kind of get smaller as it moves towards the back. Okay, so you have this big cornucopia square barn, all right? And that's Emmanuel the duck. All right, so he wants to know if he will have enough volume in his barn to have a party with all his friends. He needs 1 cubic mile of space in order to fit all his friends in that barn. What is the volume of this figure, and will he have enough space to entertain his friends? Okay, so like I said, to find the volume of one of these shapes, we're adding up a bunch of whatever the cross section is. In this case, it's squares. So if I'm adding up a bunch of squares or areas of squares, I want to go back to this formula and use that s squared. So adding up a bunch of means take the integral. All right. And then adding up a bunch of squares, that s right there, we need to define that. So I'm going to define that really quickly. So just like we learned from the area, the base here is going to be the top minus the bottom. So that's going to be the negative x squared plus 2, and then minus the bottom is the square root of x. Okay, so that's my s. So I'm going to put that here inside the integral, and I don't need all those parentheses. So that's going to be negative x squared plus 2 minus the square root of x. And then that whole thing is being squared. And then, of course, we need our dx. So this s squared piece, that represents the area. The dx represents kind of like the width. And so if I add up a bunch of those, you'll end up with the volume. And then you need limits of integration. So we're going to be going from 0 to 1. Now, we are definitely going to be using the calculator for these. So if you were to put this in the calculator, you would get a volume of 1.271, and then that's miles cubed. So he only needs 1 cubic mile, so yes, he has enough space. Okay, I know this is pretty difficult to visualize, so in class we're going to look at some actual physical models on the computer and also like something that you can actually physically hold in your hand and see. So we're going to see that in class. The main thing I want you to get used to is getting used to the formulas. So this was an application type problem. Yes, I know, a very stretched application problem, but now we're going to do just some regular old problems and we're going to get practice with each of these different types of cross sections. All right, so on the next example, we want to find the volume of a solid whose base is bounded by those equations, and then we're going to look at each different cross-section and how those are going to look. So I'm going to graph those really quickly. Okay, so I'm going to cheat and use my handy-dandy graphing tool to make a pretty picture for the video. So here's what the graph should look like, and then my red line, I drew a representative rectangle. So just to make sure y'all are clear, what you're trying to do with the cross-sectional volume is you want to make sure and find that S value. So that S that we're looking for is going to be like what we defined in the very beginning of the video, and that's going to be like your representative rectangle. So this problem says we wanted cross sections perpendicular to the x-axis, so that means that we're going to have vertical rectangles, which is with respect to x. Okay, so for the first example, we want to take cross sections that are going to be squares. So just remember the formula for square is s squared. So our volume is going to be the integral from, just look at our limits, just like when we're finding area, from -2 to 3 of that S value. So that S, we need to understand and make sure to define that. I like to define that first. So that's just going to be like we did before, the top minus bottom. So that's the negative x squared plus 4 minus negative x minus 2. And when you simplify that, we get negative x squared plus x and then plus 6. Now, if you've already defined that that's S, early in the problem, then guess what? In each of the different parts, you don't have to rewrite S. Just know that that's going to be the same S for every single piece, no matter what cross-section you're going to have. All right, so for the squares, my volume is going to be the integral from -2 to 3 of S squared with respect to X. And I don't have to rewrite the S. Then you would just put that into the calculator and we get a nice number of 104.167. All right, so now for part B. We're now going to do equilateral triangles. Now, if you remember the formula of equilateral triangles, the area is √3/4 s squared. Well, what's in common? I still have s squared, and that s is the same s as the first example with the square. So all I have to do is that the volume then would be my integral of s squared, but then just multiplied by a multiple of √3/4. So this would be √3/4 times the integral from -2 to 3 of s squared dx. So since I've already evaluated this right here in part A, then all I would have to do is say then that's √3/4 times 104.167, which is 45.1055. Okay? All right, so for part C, this is the only one that you can't do that with because with rectangles areas are not squared. So that's the only one that I'm going to have to actually rewrite and then reevaluate in the calculator. So if I have a height of 1, the heights for the rectangles are going to be constant. So you can just multiply outside. 1's pretty simple, so I don't have to show this, but I want to show it for the notes because if it was a rectangle of height 2, you would want to multiply your integral by a multiple of 2. So I'm still going to have from -2 to 3, and I'm still going to have s, but this time with a rectangle, it's not squared because it's just length times height, or length times width, sorry. So then it would look like this, and again, I don't have to write my s, and then when I reintegrate, you get 20.833. Okay, so now for D is isosceles right triangles with the leg and the base, and that was 1/2 s squared. So then all that would be is 1/2 times the integral from -2 to 3 of s squared. So then all we have to do again is just 1/2 times that original answer that I had at the top of the 104. Sorry, guys. And then for the final example, which is semicircles, that would be a coefficient or a multiple of pi over 8. Okay, and that final answer would be okay. So I know that was kind of long and tedious, but I just wanted you to see that this is actually pretty easy. But the main thing that you need to do is memorize those formulas. So the pi over 8 for the semicircle, the 1/2 for the right triangle, and then the √3/4 for the equilateral triangle. All right, so we're going to do one more example, but we're just going to do it really, really quickly. So for example 3, the only thing really different other than the equations is that now we're going to be looking at perpendicular to the y-axis. So we're going to have horizontal cross sections. So go ahead and graph those, and then we'll evaluate the volumes. Okay, so here's the graph. Now, since we're taking perpendicular to the y-axis, you could have done this one with respect to x, and actually it would have been easier. However, they told you to do a perpendicular to the y-axis, so we have to do a dy. So since I have to do that, I have to solve for x to get my function in terms of y. So I've done that here. All right, so if I want to now find that s, which I, again, wanted to find before I do anything else, and that's going to be now right minus left. So the right is going to be the positive square root of 3 minus y, and then that's going to be minus the negative square root of 3 minus y, which actually that's going to end up being 2 square roots of 3 minus y. So that's what s is defined by. All right, so we're going to do the same thing for part A as we did in example 2. So for part A, we have, we want to find cross sections that are squares. So the volume is going to be then the integral. Now be careful here, we're taking with respect to y, so we have to take y values as our limits of integration. So that's going to be from -1 to 3 of our s, which is 2 square root of 3 minus y, that squared, and then dy. All right, and then if we were to actually simplify that, I just want you to see that this would be, the 2 squared would be 4, which can come out front. So just if you were doing this by hand or something. And then the square root of 3 minus y squared would just be 3 minus y. So this actually becomes pretty easy to integrate and solve for. And when you solve for that, you would get 32. All right, so we're just going to get practice really quickly. We're not going to write the whole integrals out. We're just going to get practice with the coefficients. So now for equilateral triangles, that would be just √3/4 times that 32, which would be, I guess we could just say 8√3 is fine. All right, for part C, that is rectangles of height 4. Now that's the only one that you have to redo an entire integral. So I have a height of 4, which is going to be 4 times the integral from -1 to 3. And then my s would still be the 2 square root of 3 minus y dy. So you could actually pull that 2 out if you wanted to and solve for that one. And then D, and I actually don't have the answer for that one, so we'll just skip that one. And then D is an isosceles right triangle, so that's going to be 1/2 times s squared, which was 32, so 16. And then the final one is semicircles, so that's going to be pi over 8 times s squared, so pi over 8 times 32 would be 4 pi. Okay, so that's really it. Like I said, we're going to get help with like visualization and stuff like that in class, but just for now, memorizing those cross-sectional formulas is good.